Good morning, students. I am O.S. Chandrasekharaya, Associate Professor of Physics, working at Government First Grade College, Tumkur. So, yesterday we have discussed certain concepts regarding elasticity. The concepts which I have discussed in the last session. So, we have discussed the different types of bodies, namely rigid bodies, plastic bodies, elastic bodies. Then I have discussed the concept of stress strain. So based on this too, I have explained Hooke's law also, and also we have discussed different types of stresses and strain. So today, with the help of Hooke's law, so we can explain the stress strain diagram. So according to Hooke's law, it states that within the elastic limit, stress is directly proportional to the strain. So Hooke has conducted an experiment by considering the experimental wire. So he started taking reading. One end of the wire is rigidly fixed to a rigid support. To the lower end of the wire, a scale, pan or a weight hanger is attached. So he go on adding the load to the weight hanger so that there will be increase in the length of the wire. So the wire gets stretches. So thereby he has noted the values of stress. Stress means the stress is nothing but the load which we have added in the hanger. And strain means the increase in length of the wire. So he has taken lot of readings and finally he has plotted a graph of stress against strain. So according to this diagram, the stress increases, strain also increases linearly in the beginning. So you can look at the curve and we can explain. So up to the point A, so there is a linear increase. As you increase the stress, there will be increase in strain. So it is almost linear. That means it is almost like a straight line. So after that, as soon as you increase the load, so there will be some non-linearity that we can find with the help of the graph. So up to the point P, so there is some non-linearity. So then on, if you increase further load, what happens? So the wire becomes thinner and thinner. So finally, if you put some more load, the wire gets breaks. So the load at which the wire breaks, it is called the breaking stress, and the point A is called the elastic limit point and point B is called the yield point. So the point C, it is at which the wire becomes thinner and thinner as soon as you increase the load further and further. So it is almost becomes thinner and thinner. Finally, it snaps down or cuts down. So the stress corresponding to this point is called the breaking stress. So this is how we can explain the stress strain diagram. So after understanding this stress strain diagram, so there is one more concept, elastic after effect. You might have heard of this word or not, I don't know. So elastic after effect, it can be defined like this. There are some materials which regains its original dimension as soon as you withdraw the external force. There are some materials, so they will take some extra time to regain their original status by regaining their original condition. So this effect is what is known as elastic after effect. For example, gold, silver, etc. So these are the materials which exhibits elastic after effect. So with the help of this diagram, stress strain diagram, I hope that you have all understood. So now, so we have discussed already different types of stresses and strain. Depending upon the different types of strain, we will come across three types of elastic moduli, namely Young's modulus, rigidity modulus, bulk modulus. So I will going to define one by one. So Young's modulus, it is defined as the ratio of linear stress It is defined as the ratio of linear stress to its linear strain or longitudinal stress to its longitudinal strain. This is how we can. Young's modulus is always represented by the letter Q. Young's modulus is always represented by the letter. The unit of Young's modulus is rigidity. The unit of Young's modulus is Newton per meter square. So linear stress can be written as F by A, where F is the force and A is the area of cross section, and linear strain can be defined as small l divided by capital L, where small l is the change in length and capital L is the original length. If we simplify this, E is equal to, if we simplify this, you will get FL, F into small l divided by A into capital L. So this is how mathematically we can represent the Young's modulus. Young's modulus is always represented by the letter E, or sometimes we used to represent with the help of small letter Q. So the unit of Young's modulus is Newton per meter square. So then the second type of modulus is rigidity modulus. So it is defined as the ratio of shearing stress to its shearing strain. It is nothing but angle of shear. So it can be mathematically represented as F divided by A into theta, where theta is the shearing angle. So that itself measures the shearing strain. So this is how we can define the rigidity modulus. It is always represented by small letter n or capital letter n. The unit for this modulus is also same, that is Newton per meter square. So the last type of modulus is bulk modulus. It is defined as the ratio of volume stress to its volume strain. So the unit of the unit of bulk modulus is always represented by the letter K, and the unit of bulk modulus is also same as that of the remaining two modulus of elasticity, that is Newton per meter square. So with these things I will complete my second session. Thank you.